Begin our discussion on space exploration with an article that was released on October 30th on the year 2020 by CBC Radio. The title is Halloween Costs More Than the Canadian Space Program. Halloween won't be the same this year. Trick-or-treating will be minimal across much of the country, if it happens at all. The same with Halloween parties for adults. COVID-19 is making this scary holiday for the wrong reasons. But we could use this time to think about our priorities. For example, you might not be aware that the money we spend on costumes and candy for kids considerably exceeds what it costs to send Canadian astronauts and scientific instruments to space. The 2020-21 budget for the Canadian Space Agency is about $325 million. According to Statistics Canada, Canadians spent about $550 million just on candy and snacks in October of 2018. A significant portion of which would be Halloween candy. Of course, we spent even more on costumes, decorations, parties, and pumpkins. So it seems plausible to suggest that Halloween costs about twice as much as the space program. Looking at this diagram, it costs Canadians approximately twice as much to celebrate Halloween each year than we pay for the Canadian space program. That works out to about $8.75 per Canadian for space and something like $16 to celebrate Halloween. Perspectives on money spent in space. The space program is sometimes criticized for spending vast sums to send people or robots to space when there are serious problems to solve down here on Earth. It's true that individual space missions can cost tens of millions or hundreds of millions of dollars, but since Canada does not build big rockets, our cost as participants, which are estimated to contribute $100 million annually to Canada's gross domestic product, are relatively low. And when you look at the payback from exploring space, it can seem like a pretty good deal for less than $10 a year. On Halloween, young children dress up as monsters or superheroes and wander through the neighborhood asking strangers for handouts of candy, which we know isn't the healthiest of foods. On the other hand, for a mere $10, we get true superheroes. Canadian astronauts are living role models and have inspired young people, both while flying in space and during school visits, to pursue their dreams. As Chris Hadfield says, the sky is not the limit. Canada's key contributions in space. Beyond astronauts, Canadians also contribute to space exploration by developing satellites and scientific instruments built to the highest standards of engineering excellence. We were the third country in space way back in 1962 with Alouette 1. We put up communication satellites such as the Anik series and the RadarSat constellation, which provides high-resolution images of the ground, day or night, and traces the loss of ice in the Arctic. A Canadian LiDAR aboard the recent OSIRIS-REx mission used the laser to map the surface of the asteroid Bennu so a spot could be chosen to retrieve a sample. And another Canadian LiDAR was aboard the Mars Phoenix lander in 2008 that shone a laser into the Martian sky to track the passage of clouds. The Curiosity rover, currently driving around on Mars, carries a Canadian instrument called the APXS that uses X-rays to measure the chemical composition of rocks. And of course, there are robotic Canadarms, which rode on the space shuttles and currently operate on the International Space Station. Canadarm3 is in development for the new Lunar Gateway space station that will be placed in orbit around the moon. Not bad for $10 a year. We spend far more on beer and hockey. Now, this could be seen as a bit of bah humbugging, but in fact, it's more of an argument that we have money for many things, including dressing up in costumes and throwing Halloween parties. And if we need to make judgments about spending money that could be better used for other purposes, then we ought to be properly informed about how much we're spending and what we're getting for it. On that basis, there's a pretty good argument for Canada's space program. Happy Halloween. I want you to think about this after this article and throughout this unit. Do you think we should spend money on space exploration? And I want you to think why or why not. Why study space and the universe? Here's a beautiful image that was created by NASA's James Webb Space Telescope. This shows the pillars of creation in outer space. It drives our curiosity and leads us to what has driven us for over 2,000 years to study the mysterious, vast space around our planet. Throughout history, curiosity and the need to understand the world around us have driven people to explore. People also explore to find new resources such as minerals and places to live. People explored on land, then on boats and ships. And on July 20th, 1969, American astronaut Neil Armstrong was the first human being to step on the moon, followed by Edwin Buzz Aldrin. The pillars of creation are set off in a kaleidoscope of color in NASA's James Webb Telescope's near-infrared light view. The pillars look like arches and spires rising out of a desert landscape, but are filled with semi-transparent gas and dust, and they are ever-changing. This is a region where young stars are forming, or have barely burst from their dusty cocoons as they continue to form. Here are some definitions. Astronomy is the branch of science that studies objects beyond Earth. A celestial object is any object in space. The universe is everything that physically exists. Let's look at some famous Canadian astronauts. First, we look at Roberta Bondar. She's Canada's first female astronaut, and she's the first neurologist in space. And she was a part of the 1992 Discovery mission. Here is her badge. She was born December 4th, 1945 in Sault Ste. Marie, Ontario, Canada. She received a Bachelor of Science degree from the University of Guelph, a Master's of Science degree from the University of Western Ontario, a doctorate or PhD from the University of Toronto, and then she went to medical school in Hamilton at McMaster University, where she became a medical doctor. She spent 8 days, 1 hour, and 14 minutes in space. Some of you may be familiar with our next astronaut, Chris Hadfield. He was the first Canadian to walk in space. He served as the first commander of the International Space Station. He served on 4 missions. These are his mission badges. He was born on August 29th, 1959 in Sarnia, Ontario, Canada. He went to Royal Roads Military College. He received a Bachelor of Engineering at Royal Military College, a Master of Engineering at the University of Waterloo, and a Master of Science at the University of Tennessee. He spent an astounding 166 days in space. This is a diagram of the International Space Station, where scientists and astronauts from all around the world spend time orbiting around the Earth and conducting important experiments and installing new technologies to monitor the Earth below. The universe and the Big Bang and galaxies. People have been wondering about the origin of the universe. How did the universe begin? Is it changing? Will it come to an end? Cosmologists observe that, at some point in the distant past, the universe was extremely compact, small, and unimaginably dense. Modern satellites can look back in time, almost to the very beginning of the universe. The observations show that the universe began its expansion about 14 billion years ago. Time and space began 14 billion years ago. This statement might ring familiar in your ears. It is written as part of the opening theme song to the Big Bang Theory television show, which you might remember. The theme song was written by the Bare Naked Ladies, a Canadian band. And I'll read the lyrics to the opening of the song. I'll save you from having me sing it. Our whole universe was in a hot, dense state. Then nearly 14 billion years ago, expansion started. Wait, the Earth began to cool, the autotrophs began to drool, Neanderthals developed tools, we built a wall, we built the pyramid. Math, science, history, unraveling the mysteries that all started with the Big Bang. The Big Bang Theory. Cosmologists agree that the universe began in an event called the Big Bang. According to the Big Bang Theory, the universe began expanding with unimaginable violence from a hot and incredibly dense state to its present state. British astronomer Sir Fred Hoyle originally coined the term Big Bang as an insulting term because he didn't believe that the evidence for the theory was very strong. But now, there is convincing evidence that the Big Bang Theory may have actually occurred. What is this evidence? Well, scientists confirm the expansion of the universe with their observations of very large distances. Looking at light from galaxies very far away means that gives us a view into the past and confirms the age of the universe. Scientists observe radiation left over from the Big Bang Theory called cosmic microwave background radiation. And cosmic microwave background radiation was key in our understanding of the origin of the universe. Galaxies and star clusters. A galaxy is a huge collection of gas, dust, and hundreds of billions of stars. Example, the galaxy that our solar system belongs to is called the Milky Way. The Milky Way is called that because it looks like spilt milk in the sky. It contains at least 400 trillion stars. It's a disc-shaped galaxy with our sun located near the end. It bulges in the middle with many stars, with ribbons or arms that curve around the bulge, and is therefore called a spiral-shaped galaxy. In 1925, Edwin Hubble discovered the first new galaxy outside of our own and called it Andromeda. We now know that there are as many galaxies as there are stars in the Milky Way. That's a lot of galaxies. Galaxies can be different shapes. They can be elliptical, spiral, barred, or irregular. Here are some examples of what these galaxy types look like. Here are some homework practice questions for you to test your understanding of what we just learned. Calendars and constellations. Careful, long-term observations of the sky by early sky watchers led to the first calendars. The days are organized into a schedule of larger units of time, such as weeks, months, seasons, or years. Celestial priests and priestesses from the past studied these celestial objects, such as the sun, other stars, the moon, and the planets. Today, our year is determined by the number of days required for the sun to return to exactly the same place in the sky with respect to the background of stars. Our year is determined by the time it takes for the Earth to make one revolution around the sun. Let's define a revolution. A revolution is defined as the time it takes for an object to orbit another object. So the Earth's revolution around the sun is 365.24 days. We know that there are 365 days a year. But where does this 0.24 come into effect? 0.24 every 4 years adds up to one additional day. And every 4 years, we add an additional day to our calendar. We call this a leap year. And we add this day at the end of February. How long is a day? Your clock has 12 markings on it. And in one day, your clock hands will travel twice around your clock, meaning that one day is 24 hours. Where did this number come from? One day is the average time it takes to make one complete rotation for the Earth on its own axis with respect to the sun, from noon until noon. So rotation is defined as the turning of an object around an imaginary axis through it. The Earth takes 24 hours to make one rotation about its axis. Let's look at this diagram to summarize rotation and revolution. The Earth travels around the sun. And in order for it to make one complete revolution around the sun, it takes approximately 365 days, or a year. While traveling around the sun, the Earth also spins around itself, around its own axis. It rotates. This spinning around its own axis is called rotation, and this rotation takes 24 hours. This is one day in our calendar. So, one revolution, 365 days. This is our year. And one rotation, 24 hours, the Earth about its own axis. This is our day. Constellations are patterns in the sky. They are a group of stars that seem to form a distinctive pattern. Celestial priests and priestesses notice these patterns, assign names and meaning behind them. For example, these are the stars that form the constellation Ursa Major, or the Great Bear. Can you locate the Big Dipper within the Great Bear? The Big Dipper is a smaller constellation that is part of larger constellations. It looks like a dipper that can be used to scoop up liquids. Next, we have the constellation Orion. It's another famous constellation in the northern hemisphere, and Orion was a hunter with a shield and 3 stars that mark his waistline. Polaris is a famous star. Polaris is the name of the North Star. Knowing where to find Polaris, the North Star, helped many explorers and sailors navigate through the unknown oceans and lands. To find Polaris, follow the two stars in the scoop of the Big Dipper, located within Ursa Majora. Here's the Big Dipper. And if you look at these two stars in the scoop, they lead and point to the North Star. Check your understanding on this section by trying these practice problems. Let's look more closely at the movement of the Earth and add in an understanding of the movement of the moon. The Earth is tilted. Here is the center of the Earth, and instead of being directly up and down, it is tilted at an angle of 23.5 degrees. So as it rotates, it does so about this axis. But this axis is actually tilted 23 degrees, 23.5 degrees from the South Pole and the North Pole. This tilt is very important. It is summer in the northern hemisphere when the northern hemisphere is tilted towards the sun. So if we have this northern hemisphere and we tilt it towards the sun, it is summertime. It's winter in the northern hemisphere when the northern hemisphere is tilted away from the sun. As a result of the Earth's tilt, sunlight strikes the Earth's surface at different angles. When sunlight reaches the Earth directly, this same amount of light rays cover a small area. When the Earth is tilted, those same amount of sun rays cover a larger distance. They're less concentrated. If you think of them as bundles of heat and light, you will notice that this heat and this light is spread out over a larger distance, whereas near the equator, this concentration of light is higher and therefore keeps this area of the planet warmer. In this diagram, the northern hemisphere is tilted towards the sun, and this is our summertime. In this diagram, the northern hemisphere is tilted away from the sun. This gives us summertime in the southern hemisphere and winter in the north hemisphere. Here's some further understanding of the seasons of the Earth. The path of the Earth's orbit around the sun is not a perfect circle, it's an ellipse. Therefore, the Earth is closer to the sun in December than in June. Here we mark the solstices. We have the spring solstice, which marks the beginning of spring. We have the autumn solstice, which marks the beginning of autumn. We have the southern solstice, in which the northern hemisphere is tilted directly towards the sun. And then we have the winter solstice, when the southern hemisphere is tilted directly towards the sun. I want you to take a look at this diagram that shows the tilt of the Earth during the different solstices. There are parts of the Earth that are completely lit up. In the summertime, the Arctic Circle receives 24 hours of sunlight, whereas in the wintertime, 24 hours of night. In the equinox, the term equi means equal, and there is a time of year when the amount of sunlight and the amount of night are exactly equal. Let's look at the phases of the moon. The moon is always half illuminated by the sun, but how much of this illumination you see depends on where the moon is relative to the Earth. The amount of illumination you see is classified as the phases of the moon. The new moon is completely unlit. And a full moon is completely lit. In moving from a new moon to a full lit moon, light starts to grow from the right. And we use the expression, light on the right is getting bright. That means that we are in a period in which the moon is growing. We call this period a waxing period. Waxing means growing. When a moon is full, it then starts to decrease the amount of light. And this amount starts to decrease from right to left. So when light exists only on the left-hand side, we say that the light of the moon or the moon is getting smaller. We call this a waning moon. So waxing means growing, and waning means shrinking. Now we also have two basic shapes. We know the shape of a full moon, and then we have these moon shapes here that look like crescents. These are called crescent moons. If we have a crescent moon where the light is on the right and getting bright, we call it a waxing crescent because it's getting bigger. If we have the light on the left, we call it a waning crescent because it's getting smaller. Our quarter moons appear to be half lit. So we have a first quarter in which light is on the right, and a last quarter in which light is on the left. So if the amount of light is greater than 1/2, as it is here and here, we call it a gibbous moon. A gibbous moon means that the amount of light is between half and full. If the moon is getting bigger, it's a waxing gibbous. If it's getting smaller, it's a waning gibbous. So waxing means getting bigger, getting brighter. And the saying we use is light on the right is getting bright. A waning moon, we call it a dying moon, is decreasing in size and getting dimmer. And we say light on the left is losing light. These two expressions help us to remember the difference between the moon phases. Now the moon and the sun and the earth can line up in special ways at different times of the year. We have a lunar eclipse in which we have sun, earth, and moon lined up perfectly. This lunar eclipse is when the moon passes into the earth's shadow. And you can see that the moon is in this shadow of the earth. Here's the earth's shadow, and here is the moon. So remember, lunar eclipse, sun, earth, moon. A solar eclipse happens when the moon lies directly in between the sun and the earth. So remember, sun, moon, earth. The moon also has another interesting impact on the earth. The moon creates the tides in our ocean. Tides are the rising and falling of the surface of the ocean and are caused by the gravitational pull of the moon, and to a lesser extent by the sun, but mostly the moon. The moon's gravitational force pulls the water in the oceans towards it. When the moon is over the ocean, it pulls it in this direction. On this area and this area of the earth, we have high tides, whereas on the opposite ends of the earth, This causes the water level to decrease, and we have low tides. The moon spins around the Earth, so as you can imagine, this cycle of tides changes as the moon travels around the Earth. Try these practice problems. As well, complete any LMS activities that you have been assigned.